Thank you. So hello everyone. I'm Alex. I'm going to talk about controllable transformations in MLIR. And before I really start talking about this, and in case you don't know, it's a tutorial, so you will have to listen to me for 50 minutes. There is some material that I will need to cover for you to understand. I'm not going to explain what MLIR is or how it works. I kind of assume that people who are here at least have an understanding of MLIR as an extensible IR framework. And I would start with why do we even want to have controllable transformations in MLIR as infrastructure. And why goes back in history a bit. So if you look at a lot of successful DSLs that have been published, that are sometimes being used in production, many of them use some sort of scheduling DSL counterpart for the actual DSL they're using to program. Halide popularized the idea of having a separate schedule that's detached from what you want to compute. So you don't want to pollute your code with loop optimizations and rolling something that makes it really unreadable. And there are many follow-up works. TVM was popular for a while in ML space. There was standard comprehension that I also worked on. NVIDIA apparently uses it in a tool called FireIron, and there are many, many more. I couldn't fit all of them on slides. And actually, this idea is not really new. If we look at the literature, I could find papers from the 90s. It's probably even earlier than that. We didn't have nice compiler frameworks back then. But there was the Omega framework from 1991 that is using some sort of schedules to produce efficient programs. So looking at that and looking at all the great experiences, it's more or less clear that as the general infrastructure, MLIR wants and needs to support schedules as a separate part of the program representation. And to give more motivation, well, beyond many successful systems that rely on this, schedules are declarative. So we can actually see and understand what the compiler is supposed to do or is about to do with your program, not just rely on some heuristic that will magically optimize it. They are separable. And in cases where you have a compiler like Clang, and it takes 2 or 3 hours to compile Clang, it would be really nice to not recompile Clang every time I change a heuristic. So schedules are separable. I can have a binary compiler and give it a schedule which it will execute and give me a better optimized program. Schedules can support multi-versioning, so I can have multiple different versions, or I can execute part of my schedule at runtime, which a lot of high-performance libraries do these days. BLAS will go and dispatch based on the size. And we can generalize that idea to MLIR. And probably most importantly for me is schedules let us focus on a specific part of the IR that we want to optimize. So if I take a really big program, I work on ML compilation, so it's a big ML model. But what I really care about is that one little operation that kind of bottlenecks everything else. I can spend a lot of compile time budget on optimizing that, as long as I don't spend a lot of compile time budget optimizing the remaining 1,000 operations that are working just good enough. And it's really important to be able to target very precisely a part of the IR that we want to optimize. Well, how do we do schedules in MLIR? Yesterday I told everything is a dialect. Well, everything is actually an op. And schedules are also ops in MLIR because that's the thing we can easily add. It doesn't take much time. And we put this ops in a new dialect called the transfer dialect. I'm done with my talk. Not really. Let's look at how it works in practice and look at a simple transformation chain. I am going to be bold and make a claim. People usually make disclaimers. I'm going to do a claimer. All of the APIs I've shown screen existed as of April 17 with that commit. I actually ran all the code on the slides. I had to edit it for clarity because MLIR is kind of unwieldy, large and unreadable, but completing it a bit, you should be able to reproduce what I'm doing in the slides. And as I said, I'm working on ML, so what we often need to do is do this simple transformation chain. So I have a thing called a fully connected layer, which to compiler people is a matrix multiplication followed by an element-wise addition, plus a thing called ReLU with just an element-wise maximum with 0. And what I want to do with this, well, I want to fuse the matrix multiplication with addition to get sort of a gem, which I know it's a gem, but I want to keep the ReLU apart. Why do I want to do that? Because I happen to have an efficient microkernel for gem. not for gem plus ReLU, just gem. And if I were to write a heuristic that would say, can you please fuse element-wise into matmuls so I can map, I actually cannot map this example to microkernels because it would fuse both of the element-wise things I have. So that's the simplest problem I'm trying to solve with transform dialect. And let's go straight into IR, and I warn you, there will be some code in the slides. There will be recordings, slides will be available. So if you can't really follow, don't worry. The important things are to understand how the flow goes. So we start with a sequence of transformations. So it is transform.sequence, just an operation. It just tells, well, execute everything inside one transform after the other. That's what we want to do. We also tell it to propagate failures, and we will get back to that in a moment. But basically now we want to say, if something fails, if any of the steps fail the entire transformation. Just complain to the user, something went wrong. We could also say suppress failures. And this will be useful if we want to try multiple things. So let's, for example, say we tried to map it to microkernel, but it didn't exist. So let's go and manually tile it instead and try to vectorize. So get back to propagate. We have this sequence, and as many MLIR operations, it has a region, and region has an entry point. And that entry point is a block that takes multiple arguments. Those arguments are SSA values in the transform dialect, but they are also operations in the IR we are trying to transform. So transform dialect operates on values, which we also call handles. And these handles are, you can think of them as like operation star. It's a pointer to an operation in a different part of the IR. So here I have the root, which is like my module. I have a pointer to matmul, and I have a pointer to element-wise. Handles are typed because everything in MLIR is typed. And types, well, there are types. They describe what are the properties that are known to the compiler about this value. In our case, we know that %matmul is a lineal.matmul operation. That's what we want to do. That's what we want to transform. And element-wise is a pointer to lineal.element-wise binary. It's very nice, and it actually lets us do some static-ish checking on the transform dialect. So if instead we were to say element-wise is a unary element-wise and run this transformation, the compiler will complain and say, well, it's an incompatible type. You are trying to transform something that I expected to be binary, but you actually gave me unary. I don't know how to do that. One thing that I kind of skipped over is a handle is associated with a list of values, not just one value. So in this case, I had 2 element-wise operations. So I need to work on that list. Well, in this case, I want to treat them separately. So there is this operation called split handles that illustrates how you would transform, in a sense, IR. This doesn't actually transform the IR, just manipulates handles and splits them into 2 parts. One will correspond to the addition called bias in ML, and the second one corresponds to maximum or ReLU. So now I have 2 handles to 2 different operations that I can target independently. Handles can be casted to a different type. So in this case, I am saying, well, one of them is still a binary. Another, I'm using PDL operation, which is sort of a wildcard. It's really an operation star. And now, using those handles, we can actually go and perform a transformation. We can take the tiling transformation that we have, because the microkernel I had was like a 32 by 32, so I actually need a smaller matmul than I had before. So if I want to apply a transformation, this is done by having a transform operation. Transform operation applies to what I call payload operations, or like the operations we transform, that are associated with the handles that are passed to it. So like I have this % bias. In the previous line, I extracted it from element-wise, and I got it from the user when transform dialect was called. So that is what is passed to the transformation. That's what it transforms. And how it transforms it, well, it's in the name of the op. It's a tile, and it's parameterized by attributes. So here I have tile sizes 32 by 32. There are many more. I'm trying to keep it simple. And when we do that, when we actually run that piece of IR through the path called transform interpreter that we will see in like maybe 15 minutes, it will actually go and perform the transformation for me. So it will take the bias, so the first element-wise operation, and do the tiling. It will introduce the for all loop. It will compute the sizes based on my 32 by 32. It will keep the binary because that's how lineage works. But it will basically perform a transformation that I asked it to perform, and only do it on the operation that I asked it to perform it on. Now this transformation will return new values in the transform IR. And in case of tiling, there are two values I care about. One is the loop that was introduced by tiling. And the second one is the operation that's inside the tiling. Why do I want that? It is so that I can chain transformations. So I can apply a transformation on an operation that was produced by the transformation for it, and so on. So I can do chains, I can do trees. It's very important for composability because otherwise I would need to go over the IR and discover where is that the point in my payload IR that I actually want to transform. One important thing about transformations is that they can also consume handles. On the same example, we are taking this bias handle that's pointing to this element-wise binary. And during the transformation, we're actually erasing that operation and creating a new one inside the loop. What would happen if I have a pointer to an operation and then I erase the operation? Like everybody programs C++, or mostly everybody, like it's a deadline pointer, dereferencing that is undefined behavior. We don't want that. So we model that by consuming a handle. Well, it's undefined behavior. It's exactly what it is in the transform dialect. Consuming a handle is fine. Using a handle that has been consumed is not. And we actually have a sort of embedded address sanitizer. It's expensive, so it's disabled by default, but there is an option to enable it that would yell at you if you were to use a handle that was invalidated. So here, if I'm trying to print the bias after I consumed it in the tile transformation, it will tell me, well, an op uses a handle that's invalidated. Please don't. Let's get back to this and let's look at composing operations. So we produced the loop. What we wanted to do is we wanted to tile and fuse. We did the tiling. Now we want to do the fusion. I don't want to fuse everything in every possible loop. I want to fuse specifically the matmul I have into the loop that was produced by tiling. It wasn't there before. And that's where this handle idea is really useful, because I have my loop operation. I have a handle to that, and I can tell transform dialect, well, fuse my matmul into the loop I had before. And this will only do that. It will not go and fuse all the loops. It will not apply any heuristic. It's basically what you see in the transform is what the compiler does. It also lets me have more precise error messages. Instead of saying, well, I'm sorry, pass couldn't apply, or just not doing anything and succeeding, it could tell me if I instead were trying to fuse something into something that is not a loop. It will tell me, well, I couldn't find the next thing to fuse here. It's not really a loop. And this is the thing I was trying to fuse. And this is where I was trying to fuse it to. Continuing on our simple transformation chain, we wanted to outline it so we can rewrite the function call. So we can do just that. We have our loop handle. We say, take this loop, outline it to a function, and then we can vectorize whatever remains. Because I want to still vectorize my max. I don't really want to vectorize, or at least spend time vectorizing the function that I'm going to replace anyway. So I extracted that into a separate function so I can avoid vectorizing and doing the transformation I didn't intend to do. To talk a little bit more about handle invalidation here, this getting a loop vectorization that I have here, it applies to functions. It applies to functions because the way the transformation is currently written, I don't like it that much, but it is what it is. So I need to first get a parent, which in this case is a function of a loop. I cannot do it after I outline the loop because the loop no longer exists. So I need to do it before. We actually model that with side effects, and trying to permute this operation would be invalid in the compiler. An interesting thing, what would happen if I were to access the element-wise binary that's still in the loop? I consumed the loop handle, but I still have a handle to something inside that loop. That would be invalid, right? We erased the loop and we created a new one. It's not exactly true, but let's pretend it is. So we erased the operation, we created a new operation in the outline function. So a pointer to the previous operation would be dangling. It's invalid. And we actually handle that as well. Consuming a handle would invalidate any handle to the same operation or any handle to any operation nested inside it. It's a bit of a mouthful to say, but it actually makes sense if you think about IR. Anything that's nested under an operation you erased is also erased. So you shouldn't point to that. So trying to access that would be invalid. and actually produces a very nice and helpful error message. It says, well, it uses a handle invalidated by that operation, but you actually invalidated the parent handle. And the parent operation in IR was this, and the actual operation is this, and so on. It's slightly longer than it could fit on the slide. So with that relatively simple transformation chain, we're able to achieve this transformation where we need to do things one after another and apply one transformation to the result of a previous transformation and chain them together. Let's generalize this a bit. So transform dialect is a dialect to describe transformations in a separate piece of IR. Can be same file, can be different files, doesn't really matter. Operations is a dialect to describe individual transformations we apply. Values on which these operations operate are associated with operations that we are transforming, or payload operations. Transform operations may either read or consume operands. They always produce new operands that you can in turn consume. And consuming handle invalidates the IR that's associated with it. There is it's not really a pass, it's like a function in the IR that's called transform dialect interpreter. And what it does is mainly, like the main thing is just a loop. It goes over all transform ops and applies them, calling like a transform interface. But more importantly, it maintains the mapping between the values in transform IR and the operations and payload IR. That's mostly what it does. It can be called by apply transforms. It's similar to pattern rewriter. So instead of saying apply patterns greedily, you can say apply transforms. Same level of API. Transform operations and types, as we will see, implement transform dialect interfaces. Well, that's a way to generalize MLIR. You implement an interface, and then all the passes reason about the interface, not about concrete ops. And transform interface is really simple, just has like, hey, transform op, apply yourself to this IR. That's pretty much what it does. The entry point is a top-level transform operation with a specific trait. And basically, most operations can have this trait if they have no arguments. So if you start from something, you don't have any mapping between the handles and payload operations. So you need to start with something without operands, and then this thing itself will tell the transform dialect how to interpret the content. Can be a sequence, can be a loop, can be a set of alternatives, can be patterns, can be whatever you want it to be. So if you would like to try this out, and like I made the claim that you can, well, there is no transform interpreter pass. There is a test transform dialect interpreter pass because I actually want you to embed that to your pass, but there is this test pass. And to this test pass, you can pass additional options that specify which payload operations should be associated with the input of the entry block. So in this case, I'm saying that the first extra is bound to lineage matmul and the second is bound to element-wise binary, and that's how I essentially configure my call to apply transforms, which takes these as extra arguments. I have a semantic trick, because people like semantics here apparently, on how to do early exit. So basically, I want to stop my transformation sequence if something went wrong. But it's SSA, so I can only do control flow in the end of the terminator. So the trick is there's kind of a has failed register that is false all the time, and then if something fails, it sets it to true, and then everything else will go and check. Oh, if it's set to true, I'm a no-op, and you go to the terminator and you exit. So it's kind of semantic check. There is a multi-entry, multi-exit proposal that will be helpful here. Now I have a more complicated example. It comes from a review. So when I submitted it, I had like 5 reviews, most of them like, please talk about this. And there was one reviewer, I think it's reviewer B, it's always reviewer B, the one that doesn't like you, who told me, well, maybe if you can demonstrate how you can replicate Halide with this, it would be interesting. Well, challenge accepted, here's Halide. I will not redo all of the Halide, but I will take one example from Halide examples. It's a const2d layer because, as you understood, I like ML for some reason. And I will try to replicate the schedules I have. So if you go to this link, there is like an example of Halide. And I need to give you a really quick tour of what Halide does. Halide lets you express a sort of tensor computation as embedded DSL in C++, and also lets you schedule it using something really similar to what we have. So what happens here is it has named dimensions that correspond to loops. It has a reduction domain, which corresponds to more loops, but just reduction loops. And then it has a statement. So in this case, it has a thing called the convolution, and it's first initialized to some value coming from bias. It can be added to the end, but it decided to do it at the beginning. And then it does a convolution. Convolution is something that you would write in like more or less naive Python. You would say like convolution of these dimensions is filter times input, and then you plus add, so you have implicit looping structure around this. And that's what it's all it does. It calls the first part a pure statement and the second update statement for functional programming reasons I will not go into. And then finally there's a rel we already saw, a rel is a max. And you can think of this as yet to be defined buffers. So like convolution, it's a buffer into which we write something, and we plus add something, and we'll put loops around them. Actually, that's how it looks in loops. One thing to notice is the order of dimensions is inverted. So the last dimension on the left will be the first loop. But that's pretty much it. That's what you would expect it to be. So like you assign something to conv, you have more loops. Now we have this error reduction loops. And we do the computation when we do conv plus equals filter times input, plus some accesses. And then we have ReLU, which is like a max with 0, and we have some loops around it. And that's pretty much the computational representation that Halide provides. And then it lets you transform this. Not even transform, because these loops don't exist yet. It lets you specify how they should be generated. And I took literally the schedules I have in the example. So the first thing it does is split, and it splits the C loops that we have into two loops, CO and CI, which, if we think about it, it's kind of tiling of one dimension. It splits another dimension, so it generates more loops. Then it does a thing called reorder. So like splitting and reordering, for people who are familiar with loop transformations, is strip mine and interchange, also known as tiling. So this big thing is a kind of tiling, and it operates on what we would call a loop handler in our terminology. Then it says, well, actually, I want to vectorize my loop with this vec size, where vec size was defined to be whatever the platform was supporting. I think it was AVX 512, so it's like 16. And then we can unroll loops. It's still on loop, so we can unroll one loop, we can unroll another loop, and then finally we can tell the compiler to execute these loops in parallel. The rest of the schedule starts with this compute at, and it's one of the hardest things to understand here, because it tells the compiler to compute a part of the value at a specific location inside the given loop. So here it says, now that I have scheduled ReLU, I want to compute the convolution that precedes it inside this loop. So what the compiler will do here in Halide, it will go and look at the loops that correspond to the convolution. We'll try to match them to the loops that are already available at ReLU, and inject the missing loops based on the iteration space. If you're familiar with loop transformation, that sounds suspiciously close to fusion. It's not exactly loop fusion, it's producer-consumer fusion, but it's still the same idea. And what it does next, it goes and vectorizes the loop. C in this case, it unrolls a bunch of loops. It goes to the update part of the statement with reductions. It reorders it in the same way. It vectorizes again, it unrolls even more. It produces like 10,000 lines of code. I'm not joking. And it obviously doesn't fit on the slide, but like it unrolled a bit, but what it did was actually tiling and fusion and some vectorization and some unrolling. That's the schedule, and they claim they have very good performance on this. I couldn't reproduce it entirely, but I was on a slightly different platform. But I could get actually better numbers with MLIR. So now that we have hopefully understood what it is doing, there are two possible approaches here. One is, well, we have loops in MLIR, so we can introduce absolutely identical transformation ops on loops, and like literally have Halide schedule one by one. Or we can try mapping these transforms to an MLIR operation that exists. Since it's a tutorial, you're supposed to learn something, I left the introduce identical transformation as a homework. So I will focus on that. If somebody is interested in adding loop transformations, please do. I'm not going to go into details because it's actually harder than it looks like. And I'm going to map this to transformations we already have on an abstraction called lineage. You heard about lineage several times today, yesterday, probably know about it. It is a specific instance of what we call structured ops. And I will just throw this scary slide at you with a lot of code and try to explain what it is. And it's structured ops for dense algebra. And why it's structured, it's because what it actually does, it tries to encode structure of our computation that makes it easy to reason about. So in this case, it operates on a kind of implicit iteration space. Again, there are no explicit loops, same as Halide. But the iteration space is derived from the shapes of inputs and outputs. It also says these two are parallel. Similarly, it has a structure of data access. So it says, well, when we are accessing the first of the buffers, we use these hypothetical loop iterators as subscripts, and then the second use others, and the third, and so on. So it kind of has this compact representation of the structure, and then the computation itself, it's performed on elements. And actually, to transform it, it doesn't matter what it is. We just copy it over all the time, and we only act on this generic representation that corresponds to loops. So if you think about it, it's really similar to what we've seen in Halide. That's why I want to map it to lineage. Its structured offset operate, like implicitly iterate on the input data. So the iteration space is kind of defined by the data you iterate over. The data access patterns are captured in a closed form. In our case, it's an affine expression because that's what MLIR had. It can be something more complex, but that's what we have. It has support for accumulation, and it does so by having a reduction loop. Again, almost the same as Halide. It doesn't need complex analysis to do tiling or fusion because most of this information is readily available. We know what the iteration space is. We know what the access pattern is. It's easy to do producer-consumer fusion by basically inverting and composing the access map so you know what is the subdomain of the producer that you need in the consumer. Also keeps loop structure implicit. So really, it's a very, very close match. It was pretty much inspired by Halide and similar technologies when it was designed. And I put a little remark here that the concept itself is not specific to dense linear algebra. Structured ops is about structure. And it actually helps us do transformations because if we can understand that structure, that's how we do transformations. And that's also how we control them. So let us look quickly at the transformations we want to do. So we have this generic, and we want to do tiling. And actually what tiling does is the first thing that produces loops. Until this point, we don't necessarily have loops in our input. So the first thing tiling would do, it will go and produce loops. And if you actually want to convert a linear operation into loops, what you do is you tile by one. You go to a tile size of 1 by 1 by 1 by 1, so you introduce just loops operating around the scalar body. Fusion is relatively simple. So once you have a loop, because you need a loop so you can fuse something into it, well, you can go and say, well, who is the operation who produces the data for me? Ah, that one. Now, I'm accessing the data using this map. What is the subset of that operation that produces this subset of data? It's a relatively simple computation that we can do and say, well, that's the subset that I need of the producer operation. If it happens to match my iteration domain, I'll just copy it over. If it does not, I will also introduce additional loops so my iteration domains match. Vectorization is trivial. Like when we have a parallel loop and we know it's like the last loop, what we do is say, instead of this being a parallel loop over I, we just say there's no loop and it's just a vector. That's almost all it does. Loop unrolling is surprisingly a loop transformation. Actually, you need a loop that will unroll by stupidly copying over the loop body multiple times. And that's pretty much all we need to reproduce that Halide schedule that you've seen. So let's look at two things in parallel. We know how sequence works. We more or less understood how Halide works, so let's just try literally replicating it step by step. So the first step was split. Split is essentially tiling where you don't permute dimensions. So we have this split of some dimension that splits it into a loop iterating over vec times tile w. That's almost exactly what we write in transform dialect. So it's tile to for a loop. That's how it's called. It takes a ReLU, same thing, and it supplies 0, 0, 0. We ignore the leading dimension. 0 means no tile. And then the dimension that corresponds to C, the force in my case, is tiled with these sizes. We could think that, well, we can go forward and implement the next split as another tiling. Well, it's not exactly true, because if we did that, we would introduce a loop around C then X. But what we actually want to do is we would want to reorder that. So we have C, then N, then Y, then X. And we cannot do that, because these loops don't exist yet. So instead of simply introducing tiling, and that's where it starts to diverge a bit, we need to use tiling by one so we can introduce more loops. So we use this tiling by one to introduce more loops so we can reorder them later. But actually, if we introduce loops, we don't ever need to reorder them. We can just introduce them in the way we want them to be ordered in the end. So what happens here is we have several tilings that produce the same loop structure that Halide would have produced by splitting the dimensions in their natural order, because our representation does not have a loop order. We can introduce it the way we want. And then we would want to vectorize, because that's what Halide does. But at this point, we cannot vectorize it yet, because as we've seen before, vectorization applies to entire functions, and we have not finished transforming this thing yet. So let's look at this compute at instead, because that's really the complicated one. And as I mentioned, this compute at is a producer-consumer fusion, which is exactly what we have already implemented in Linux and available as a transform operation, transform dialect. So we can say, well, take this convolution operation, which is exactly the same as on the left, and fuse it into all the loops that we produced before, because we produced multiple, and it, like, instead of saying compute at that loop, it says, well, fuse into the first loop, then the second, and the third. I only had 3. We need to do the same for the bias, because we don't separate between this like pure and update. It's kind of too complicated. We always have a handle to something. So we need to do it for the second operation. And then it gives us the same fusion structure. It's exactly the same structure. I checked the code at the output. It's almost the same code when you look at the MLIR. Then we do reorder. Well, we kind of know how to do reorder. We tile by one to produce the loops in the order we want them to be produced. So we produce the n loops that we want. Then we produce all the reduction loops by putting one in the corresponding dimension. And then we produce y and x, and it actually gives us exactly the structure we want to have. The last one is tiled by 16 instead of 1. And why is that? Is because I intend to vectorize to 16. And now I think I can vectorize. I produced my loop and fusion structure. The last loop is a loop over 16 elements. I can go and turn that loop into, like, we know it's a parallel loop, so I can just go and turn it into no loop over a vector. Then we need to do some unrolling. We could have done it earlier, but we can also done it later. It doesn't matter, as long as we still have loops. So we can do unrolling. Same applies everywhere, so it can complete the schedule. And for that, I have these handles. So it's perfect. I don't want to unroll all loops. Unrolling is one of these complicated transformations in the compiler where you have a very complex heuristic. Do I want to unroll here or not? By how much? How much it will affect register pressure and so on. Here, I don't do loop unrolling based on something. I unroll specifically the loops that were produced by this tiling. It's great. There is one problem. The loops I produced are these parallel for all loops. And unrolling does not understand those. It only understands for loops. And I don't have those. I actually don't have a transformation to go from one to another, which is why I would need to extend the transform dialect. Let's look into that a bit. So we want to define a new transform op that takes a handle to an SCF for all parallel loop operation and triggers some rewriting that produces a nest of sequential SCF4s. That's what I can unroll. And then it needs to return handles to the ops it produced so I can chain transformations on this. If you've seen how to define operations in MLIR, you can sleep for 5 minutes. If you haven't, that's how you do it. So you define an operation in TableGen using the ODS syntax. So it's an op. It's called tutorial.forAll24. It belongs to the transform dialect. It's useful to know here that we can actually inject ops into somebody else's dialect. We say that this op implements a transform op interface. It also implements memory effects interface. Remember how we invalidate things, and that's what we need for it. And it takes as arguments a handle type. to the transformation target. It also produces new handle, so it's a variadic list because I can produce one or more loops depending on like for all being a simple for or multi-for. So it's a variadic handle type transformed. This looks exactly like any other open MLIR, just an op definition. Now what I need to do is trigger this rewriting from SCF for all to SCF for. And for that, I need to implement the method declared by my transform op interface. There's only one. It's called apply. This method returns a thing called diagnosed silenceable failure, and I will stop a bit on it because I think it's really useful in all of MLIR and we should promote it. But for now, it's restricted to transform dialect. And it's a tri-state result object. It can be a success, nice. It can be a definite failure, which corresponds to like logical result failure, but it can also be this silenceable failure. It means something has gone wrong, but we can recover from it. It also contains the information about what exactly has gone wrong. This function takes two things, transform results. We are supposed to populate it with the values that will be associated with the resulting handles, and the state. And the state it's basically access back to the interpreter, so it tells you what a value in the transform IR is mapped to in the payload IR. You can think of it as like a very big, dense map. And what we do in that function, well, first we want to understand what is the target. So what is the target value mapped to? So state get payload ops does that. If it's more than one, I'm lazy, I don't want to handle that, so I'll just emit the silenceable error and let somebody else handle it. Then if the op is not a for all, I will also complain. And this is actually a very common thing where I would complain if it's not an operation of the right type. So instead, we would specify the type. We would say, well, my op actually expects a concrete op type, which is SCF for all, and then the infrastructure will handle the type verification for us. So instead, if we specify that, we can just expect it to be a for all op. We can directly cast. It should never fail if the verification succeeded. Do the actual rewrite. I will spare you that. It's straightforward rewriting of IR in MLIR. And then we associate the results. So it produced a list of SCF4 loops. So I'm saying results set, first results correspond to first loop, second corresponds to second loop, and so on, as many loops as we have. The second thing we need to implement is this get effects thing. And the effects we have are the things we discussed. We can consume handles, we can read handles, we can modify the payload IR, or we can only read the payload IR. That's exactly what I will say here. So it consumes the target handle, it produces the resulting handle, it always does, and it modifies payload. It modifies payload so we don't kind of reorder transformations that should not be reordered. This is also a common thing. So there is a functional style transform op trait which says if your transform consumes all the operands, produces all the results, and modifies payload, it's kind of functional composition. You destroy the old one, you produce a new one, you keep composing. It's functional style. You don't even need to write this. That's all you need to define a new transformer. That's literally all. There are more interesting things like transform each op trait or possible top level or navigation op trait. They're documented. I will not spend time on them. Now that I have this op, it's all good and nice. So far I was working in upstream MLIR. It's a bit annoying to push stuff to upstream MLIR, especially like getting into this transform dialect that Alex owns. You know, he'll complain about this design. So I just want to keep it in my tree and like not care about anybody's opinion. And it's really easy. Well, we can't just define an op in somebody else's dialect, except that we actually can. We have this dialect extension mechanism that lets us inject ops and types, basically anything into dialect. In that, well, we have this transform dialect extension. We need to say which dialects we are going to generate. In our case, we are going to generate SCF. This is necessary for like dependency management purposes. It's not specific to transform dialect. And then we do register transform ops. And then the body of this is exactly the same as if you had a real dialect. If you have a dialect, you need to list all the ops the dialect has. Now we call this register transform. It just does some additional verification and adds the op to the dialect. You write your CMake, make sure the table gen connects. It takes like 10 minutes. And you have your extension. You load the extension. It works with the upstream transform interpreter pass. It works with all the other extensions that are loaded. So it's not strictly necessary for out-of-tree projects to do this, but it's kind of nice, and in tree we just didn't want to have double the number of dialects we've seen. We already have too much. We can also have a custom pass if we want to. So there is this transform interpreter pass base, where run on operation is literally these 3 lines. That's all you need to basically have your own pass with your own extension in your own project. So now with that, we can actually have that. We can have our additional op. We can get back to Halide. I had this problem where for all loop is not something we can unroll. So now that we have this newly defined transform tutorial for all to 4 transformation, I can have it there. My loop 1 is produced from tiling, so it actually corresponds to 3 loops introduced by tiling. It returns 3 handles. And I'm going to unroll the last one and the second to last one and basically replicate the schedule. Here is yet another small problem. I have a PDL operation as a result of tile to for all. It's untyped. But we just set the requirement to be an SCF for all. And that's where I have this handy operation called transform.cast, which the only purpose of which is to change the type of a handle. And when you try to assign values to this handle, the infrastructure will go and perform verification if it is the type that we expect to be assigned and complain if it's not. So putting it all together for Halide, well, there is a couple of, there are actually more transformations, but many of them can be mapped. And split and reorder, and actually split and reorder and vectorize, more or less, are this tile to for all. They're all a way to define tiling. Unrolling, it's unrolling, and compute add is fused into containing op. So I actually did the experiment for you. I don't have nice fancy graphs. And with Halide, concrete example on my machine, I got like what it was, 100-something milliseconds for a convolution to D for like ResNet sizes. And with this, I literally replicated the schedule. I got to like 28. So I checked, we vectorized slightly, but actually lower vectorized code better. And we have slightly better access patterns. Halide is also kind of flaky performance-wise. But at least I was expecting, yeah, it would be nice if I get in the same ballpark. I probably missed an optimization. I did not expect it to actually be faster. It was. There's a bunch of things actually swept under the rug here. And one of those is structured ops are defined on tensors. Halide kind of works on buffers. We have a bufferization process. It's global. It applies to the entire module. And it's currently not controllable or not controllable enough for my taste. So what happens if you call bufferization from transform dialect, it will destroy all the handles and you need to rematch things, so you need to rematch loops. But again, I managed to have this. I will have a textual version of this tutorial, so you should be normally able to replicate and reproduce these results. Okay, reviewer B, are you happy? I hope you are. We can replicate Halide. So if you are not asleep yet, some of the more exciting stuff that we can do with transform dialect and some of the actual motivation we had to do it is we can do much more things because it's a dialect, it's very extensive. We can have not only operation handles, but also value handles because, well, we have values, we want to act on values. If we want to do memory transformations, we would want to do them on value that corresponds to memory, not on some operation that may or may not produce memory. We can have a thing called transform parameter that we'll understand why in a minute, that refers to an attribute in the IR or like properties now, I didn't check. And this maps really easily to the parts we've seen before. So if we had get or set payload ops, we can have get or set payload values, we can have get or set parameters. So it's really transparent. And now that we can combine this, it becomes more powerful. We are thinking about also having a handle to blocks and regions. But even if we don't, we can kind of mimic them by saying, well, it's a second block of a third region of that op, where we have a handle to the op, and these things are attributes of the transform operation. Parameters are called parameters because they will let us parameterize transformations. So in all my example, that first one was simple, the second one I took from Halide, all my like tile sizes were statically specified, which may be a good idea, which might not necessarily be a good idea if we don't know the sizes of the program or we don't have the machine learning. So what we can do is we can have a pseudo transform op that will take a handle to what we are transforming and produce our tile sizes by looking at it. So we can externalize the tile size computation heuristic, and we can have more than one. We can have this default sizes for op. We don't actually have this one. Please don't try to reproduce. We can use a machine model. We can have like a handle. This is my machine. And this is my op. What would be the right sizes to use, or what is the amount of fusion we want to do here? We can plug in machine learning. Use ML magic. Give me what are the best sizes you learned for this problem. We can do even better. We can emit code that computes those sizes at runtime. Because actually this thing supports parametric tiling, so we can tile with a size that we do not know at compile time. It will be a value. And we will emit the IR that computes the value. We can build a nice little decision tree, which is what libraries do. We can specialize more. We can specialize on the amount of fusion. We can specialize on other like unrolling transformations. Very nice. I did mention rematching. So we can use that failure suppress to implement matching, like PDL style matching or even more, with transform dialect. So now if my transformation is only succeeding if the result has, if the operand, sorry, has some properties, then I can say, well, if it failed, I will try the next one and the next one. And that's how you can implement matching. So we can say, well, if my op has a name linear generic, well, then succeed. And maybe this thing will produce a new result. I can go further and say, if my op has a name linear generic, and also it's a structured op where all the dimensions except the last one are parallel, then succeed. Furthermore, all of that, and if the last dimension is a reduction dimension, then succeed. But not only succeed, also give me the size of the reduction dimension, because I'm going to GPU, I need to know if it's like 32 or less, so I can do it in one warp, or it's more, then I need some more complex mechanism. I can, that's exactly what I was saying. So it can compare, and only then it will succeed, and in the end it will yield the op. And it will yield the op that will be empty if it failed, because when we fail, we just have that register, it's a no op. Or if it didn't fail, it will contain something, and then if it's not empty, we will go and transform, and it will be fine. And if it is empty, all of the transforms on empty are no op, so we'll do nothing. That's how we can match and control transformations in the same dialect. Isn't PDL enough for that? Well, not for this one, because what this does is all that's written on the slides. I will not read that. I will not let you read that. But it's a long thing. It's really complicated to express that in PDL as of today. Moreover, we can probably see PDL matching, at least, as a special case of the transform dialect. We can do more. We can actually connect PDL, because we can define more operations. So we can say, if we have PDL patterns, like let's match test some operations, say PDL.rewrite with transform dialect. We can then, inside the transformation sequence or any other container, say, well, PDL match that, and if that matches, do something. So it will return the operation that match this PDL pattern. It will do all the PDL magic, compilation, interpretation, whatever you want, and combine it with the transform dialect. It is certainly not limited to structured ops. There are downstream extensions that I'm aware of for affine loops and member-level optimization. There are probably more that I'm not aware of. I hope there will be yours by the next EuroLLVM. It's really easy to add. And it's not even limited to ops. Out of one can go and define the pass pipeline transform dialect, which is the pass pipeline I showed in the beginning. So we have a built-in module, inside that we have a function. On that we have test transform dialect interpreter, and we do some binding, and then we canonicalize because we don't like an uncanonicalized code. These do not exist yet. And that's my basically final future work kind of slide. Now the way we think about transformations is we have a compiler. It's more or less a black box to most people, even us. It takes some IR, it does something inside, it does transformations, and it produces a transform layer. It's very nice, it works great when it does, but when it doesn't, especially when we are developing the compiler, we want to kind of play with what it does and experiment with different things. We would like to be able to control this a bit more. We would like to tell, well, now maybe if you unroll that specific loop a little bit less, it will be better. So now we can do this transform IR as performance experts. We can also have this transform IR in some database that we can search over and see if there is something that matches our input. We can do AI, Google, Bard magic, generate the transform for me. We can do even more. We can have the base compiler, and we can have the transform IR with some additions that the compiler does not know about, and use the recently added MLIR plugin mechanism to actually plug in the extensions into the compiler as a library and plug in the script in the compiler. So I'm really excited about being able to tune and control what happens inside the compiler without actually recompiling every time. Thank you.
Thank you very much, Alex. That was incredibly insightful. Thank you. We have time for questions.
Thank you very much for the talk. I had just one question. So the examples you showed right now, they're very much like loops and linear algebra. Are there any funky examples right now of doing transforms on, maybe on transforms or transforms on, I don't know, maybe something from the circuit dialect? Can you give some examples maybe, please?
So I don't have transforms on circuit. I did play with transforms on transforms. That's actually why, incidentally, they have side effects because I realized if I run CSE on transforms, they don't have side effects. It's a no, but it removes all transforms. So one of the things I thought of is kind of transform specialization. So when you have these parameters, and you know that your parameters are sizes and we only care about sizes more than 32, you can do constant propagation through that. And you can simplify your transform. Or you can say, well, I'm gonna go and insert sort of a transform if. If size is more than 32, do this, otherwise do this, and you can propagate that. And I'm toying with like building a sort of decision tree out of that, using like different transforms. Other things we can see like permuting them and so on. So you can do transforms on transforms. There is some limitation when you want to transform the script that is currently running. I just don't want to deal with that, but if you want to, please come and write it.
Yeah, thank you for the talk. I was wondering, you implement a new transform operation using C++.
Yes.
Is there a way to implement new transform operations using the transform dialect?
If you define transform operations that correspond to really low-level manipulation, so if you have like replace operand with that value, where value comes from the handle, sure you can.
Okay, and that leads into the second question. Like, is there a basic alphabet of transform instructions that could create all the rest of the dialect, maybe?
I suppose, but basically, if you take the entire operation API from MLIR and expose each function as a transform operation, well, we have recreated the entire API, so we can do whatever it can do. It's probably not a great idea, but as a research project, certainly I would not necessarily use it in real. It's going to be terribly slow, and like I wrote the code, I know it's slow.
It's not on. Yeah, it's on. Thanks. Yeah, I love that you took the Halide example because I remember when Lina was not even 1 year old, so that was like 3 years ago. I was like, why don't we rebuild Halide on top of Lina and show what we can do? And I guess we needed to build a dialect first because we couldn't just do Halide without building a compiler with MLIR itself, and that took 3 years. So thank you, Alex. At least we have it now. I wanted to follow on what Anton was doing, because fundamentally, I'm not sure how to position the transform dialect with respect to PDL. And you just mentioned why that would be a research project to expose the API of modifying MLIR. But isn't it what we did with PDL? Isn't PDL originally really the ability to write some sort of bytecode that can do arbitrary modification, exposing the operation API? And then transform seems like almost a layer on top of PDL, almost like syntactic sugar on top of PDL. yeah, so I wonder if like there's not a mesh of those that.
Yeah, so we actually thought about that, and basically why we even have the transform dialect is the transformations we can do with PDL are these lower level transformations where you can like combine two ops or update a value, update an attribute, that kind of stuff. And we are looking at the significantly higher level transforms that are doing like hundreds of lower level rewrites. One of the things that I had in my original proposal is we can eventually lower these to PDL. This is something that can be explored. What stopped me there, the entire system becomes very complex. So we start with transform dials. We are going to go through multiple levels of abstraction before we hit PDL because MLIR, we need to have like this crazily complicated lowering diagram. And then when we hit PDL, it will go into the PDL interpreter. So basically, if something goes wrong, especially in the like transform development stage, it's really hard to do something about it. So if my transform failed, like or crashed in the middle, how do I debug that? And here we get C++, so you just attach a debugger and run with it. And otherwise, it becomes more complicated, but it's certainly possible. And maybe one day it will happen. Maybe there's one is a subset or a superset of another. So I hope that answers.
I don't mean that we need to turn everything into PDL, right? Those for me become some sort of intrinsics. And the way to extend PDL, by the way, can be to inject, like already we see with PDL, right? You can inject C++, but there are things you can express with native PDL. And if we take your last example where you expressed things with transform, but then you had to create a new op and a new C++ handle, and you mentioned the plugin mechanism where you have to build a shared library and inject it in the process. Like there are likely things where you would be able to express them with PDL without having to, because the plugin mechanism is like Linux specific, doesn't work. Like it's very fragile and complex, right? PDLL allows you to kind of decouple this. So anyway, yeah, we'll get there.
It's something that should be explored. For now, it's not like the immediate thing that we should work on. Yeah, plugins is like more of an extreme case. Plugging like C++ callbacks from PDL, like ultimately, if I were to write the transformations having PDL, it will be only C++ callbacks, and then what's the point of like orchestrating them through these extra layers of abstraction?
Right. Composability was what Anton was saying.
We need to wrap up.
Okay,
prepare for the next presentation. Sorry.
Thanks.
Let's thanks Alex again. Thank you very much.